y over 3 plus y cubed over 2, integrated from 0 to 2, so we get y squared over 6 plus y to the 4th over 8, evaluated at 0 and 2, 2/3 plus 2, and thankfully we get the same answer, which we should. So R will be this rectangle, 0, 1, 0, 1, and the function is going to be x squared minus y squared over x squared plus y squared squared dA. Now, we're not actually going to go through the whole laborious process of integrating this because we simply don't have that kind of time, but I will simply jump straight to the punchline. If you try to apply Fubini's theorem to this, so depending on whether you integrate with respect to x or y first, the answer that you get is plus or minus pi over 4. So you get pi over 4 integrating one way, minus pi over 4 integrating the other way. So what's the problem here? Fubini's theorem says you should be able to choose either way, either sequence of variables, and you will get the same result. So why might this function be such that Fubini's theorem does not apply?
End up being a trig.
What?
Does it end up being a trig when you?
The way you evaluate it, it does help to use trig. You end up, well, actually, when you integrate with respect to the first variable, whichever one you choose, you end up making a substitution involving a tangent. But has someone else started to say something?
Not continuous.
Yeah. So we have here the limit as x and y go to 0, 0 does not exist. Right, this function fails to be continuous on the entire rectangle. So because of the problem at the origin, which is included in the rectangle, Fubini's theorem does not apply, and therefore you're allowed to get different results. So you have to be careful. This function looks fine, and if you integrate it over a rectangle that did not include 0, 0, you wouldn't have any problem. But you have to make sure that your function is continuous, and you have to include the boundary of a rectangle. That's the key point here, because in the interior of a rectangle, there's no problem. But once you take the boundary into account, there is. Okay. So, nice recipe for a trick question. All right.
Would you actually like us to work it out both ways to show that they don't equal, or can we just say since it includes the origin, they're not going to match? Or?
So if you could say, well, it's not continuous. I guess it would depend on what I was asking. But if I were asking it, does it be? I can compute the volume of the solid. It's bounded by these planes, y equals 0, y equals 2, x equals 1, x equals 4, z equals 0, and x plus y plus z is equal to 8. So a lot of problems involving double integrals are defined in this way. You have to compute the volume of a solid, and you're given a set of equations that define a solid. So often one of them is going to be a surface that's defined in terms of an equation involving x, y, and z being equal to 0. And a lot of the equations will be very simple equations in this form that define planes. And these will give you your limits of integration. Now, this doesn't apply in this example, but in some examples you may have to look at, well, where do some of these equations intersect, so to make sure that you have all the limits of integration that you need. Okay. So the volume is going to be the integral from 1 to 4 in x, 0 to 2 in, in y, and z equals 0 defines the bottom plane here. You just need to solve this for z. So it's going to be 8 minus x minus y dy dx. So that is the setup of the integral that's going to give you the volume. On the other hand, suppose I had something else here. Suppose I had z equals some other function of x and y. Then I would subtract the two. But if I wanted volume, I have to be careful how I subtract. So, so for instance, let's suppose instead of this, I had z equal to 22 plus sine x plus y, let's say. So if I wanted the volume of the solid bounded by all of these surfaces, almost all of which are planes, what would the setup of the integral be? And this is similar to back in 167 when you're computing the area between curves. It's a similar principle. So back then, how did you have to go about it? You had two functions of x, and you had to subtract them and integrate the difference. But how did you know which to put first? They don't remember from back then?
Was it the one that was
That's the
higher?
function, wasn't it? But depending on whatever shape it was the function that was on top, I guess.
Yeah, you might have been talking about a different problem originally,
Right.
but yeah, top minus bottom. Same idea here. Which is going to be on top? Anyone care to take a stab at it? Yes, it's going to be this one. And the reason why is, if you look at the possible range of values that x plus y can have, right, x plus y is going to be at least 1, and it's going to be at most 6. So z, based on, so the values that z will assume are these values of x and y. So on this rectangle are going to range from 2 up to 7. But here, this function ranges from 21 to 23. No matter what x and y are. So this function is going to be on top. So for this, the volume would be 1 to 4, 0 to 2, 22 plus sine x plus y minus 8 minus x minus y dy dx. Alright, so that's what top minus bottom will give you. Same idea applies here, the volume between two surfaces. It's probably mentioned in a later section, but I wanted to make the example a little more interesting. Now, let's take a look at just one piece of this, because almost everything here is going to be quite simple to integrate, and what we had here, this is no different than what we saw in the last example. So let's not do that. But let's focus on this part right here. So integral from 0 to 2, integral from 1 to 4, sine x plus y dy dx. So